Hi, my name is Will Crawsick, Scientific Services Manager at Chemical Computing Group. Today I'd like to demonstrate the tools that we have in Mo for fragment-based drug design. In this example we'll be looking at medicinal chemistry transformations, which is a useful application when we'd like to make bioisosteric replacements directly in the binding pocket. So let's get started. So the first thing I'll do is use the Open button to retrieve the file that we're going to be working on from the sample mol directory. So I'll just navigate to the file, select that and hit OK, and I'm greeted with this Load PDB file panel. This allows me to select what data to load into Mo. Here I'll accept the defaults and we see our structure appear in the main Mo window. The structure itself coloured by a secondary structure with helices in red, beta sheets in yellow and turns shown in blue. Now, before we can actually start our fragment-based drug design, the first thing we need to do is prepare this model. It's a raw PDB file. Typically, it won't have any hydrogens. Perhaps the charges have not been calculated. There might even be some missing loops. So I'm just going to go ahead and select QuickPrep, our automated preparation wizard, which is going to handle all of that and ensure we're working with a high-quality structure. The panel itself comprises three main sections. The first handling the preparation and cleanup of the structure. Second sets tethers and restraints. The third handles refinement. Again, I'm going to accept the defaults, click OK, and I get a progress update at the top left of the main Mo window. Now, before I move on, I just want to take a moment to explain what QuickPrep is doing in the background. So the first preparation stage ensures that we've got a complete model. What we do here is ensure that we're adding in any missing hydrogens, charges, and side chains. If there are any missing loops in our model, up to 10 residues in length, they'll be grafted in. Protonate 3D optimizes the ionization states of the bound molecules together with their side chains. It also generates a hydrogen bonding network through the placement of polar hydrogens. By default, we're going to tether the atoms within the active site, and the reason that we do that is to ensure that we can retain the original geometries of those atoms as captured by crystallography. We don't want to lose the geometries of those atoms to processes such as energy minimization. Likewise, we can fix any atoms that fall outside of the active site, and we can do that for reasons of computational efficiency. The final step in QuickPrep is the refinement stage, which performs an energy minimization to ensure that we don't have any clashes in the structure. Now, I see the message has gone from the top left of the main Mo window, so I'm just going to cancel this panel, and now that we've got a prepared model, we can get familiar with the complex, starting by having a closer look at how this ligand is interacting with the receptor. So I'll do that by hitting Site View, which isolates the ligand together with any residue within 4.5 angstroms. And next I'm going to want to adjust the rendering, which I can do using the System Manager. So I'll just open the System Manager and pin that to the main Mo window as a means to manage all of the data that I have in the system. From here I can hide and show different atom sets, make selections, generate surfaces, and also render. So here what I'll do is just use the rendering controls to hide the ribbon, and I'm going to colour the ligand a bright colour. So with that, we've got our system prepared. Our ligand is now ready for us to explore the medicinal chemistry transformations. So what we'll do is we'll perform bioisosteric replacements to the ligand directly in the 3D receptor pocket. And we're going to do that whilst preserving or enhancing the ligand properties. So this is a good application for when we want to make very minor and focused changes to a structure. So I'll just go ahead and open our panel, which I find within the Fragments submenu. So here, what we'll do is select MedChem Transformations, although you can see all of the different operations that we have that fall under the umbrella of fragment-based drug design. So that opens our panel comprising four main sections. The first allowing us to define the system in terms of ligand and receptor. The second allows us to define the type of operation that we'd like to perform, and here you'll see the same operations as we saw within the compute menu. The third allows for filtering, be those 2D descriptors or sophisticated 3D pharmacophore filters. And the final part allows for scoring and minimizing our structure. So I'm just going to move this panel to one side, and next we can set this up. So the panel itself is guiding me to select a ligand atoms subset if I want to restrict the transformation. So as that suggests, the default is going to apply the transformation rules to all ligand atoms, but I can select a subset of the atoms to which we're going to perform the operation. So here what I'll do is just raise a 2D schematic of our ligand, which will allow me to draw a selection box over the atoms that I'd like to perform this operation on. So if I just go back to the panel, I see we've got our 33 atoms selected, and next I'll move on to look at the filters section of the panel. And here I notice that the check filters button is coloured red, so I'm just going to use my mouse to hover over this to raise bubble help, and bubble help tells me this button is coloured red if the ligands do not pass the descriptor filter. Now I can get further information on this by clicking on the check filters button, and it displays that the molecular weight of the current co-crystal ligand is 528. And the reason that might be a problem is because our descriptor filter has a molecular weight cutoff of 500, so the existing co-crystal ligand would not pass this filter. So for that reason, I'll just push it up to 600 manually by typing in there, and then I'll move on to the final part of this panel, where I can minimize the generated structures within the receptor environment. So I'll just opt to toggle that on, and I'll also have a score written to the output database. So I can select between these scoring functions, and I'll choose GBVI WSA. So this is going to score each newly generated structure within the receptor environment as if it had been docked. So I'll go ahead and run the search by clicking search, and I get a message at the top left of the main window which is telling me that the calculation's been initiated, and also a database viewer is written where the results will be written. So the database viewer is the one of the major window types that we have in Mo. We use it to display database entries, or in this case, database results. It's also our launching point to the various tools that we have in Mo. So for example, we can calculate fingerprints here for our newly generated ligands, should I wish. The database viewer itself looks and feels like an Excel spreadsheet, but if I just drag this outmol field open, I can see it actually contains the 3D structure of our newly generated structures. So I just want to go back to the panel for one moment just to explain this iterations button here. So here iterations by default is set to 1, but if I set that to 2, what it would do is reuse the replacements that have been generated in that first run, and again apply the bioisosteric replacements, which would further diversify our ligands. If I just go back to the database viewer itself, we can see that the transformations or the rules that have been applied are written here. So I'll just double click on one to show the type of reaction that we have encoded within this database. So it's a fundamental algorithm of match and replace. When the algorithm finds a substructure like the one on the left, it will generate an analog of our original ligand, replacing the fragment with the fragment on the left with the one on the right. So as I say, a fundamental algorithm of match and replace. If multiple matches are possible, all will be applied. We can customize the rules that are included within this transformation set so that we can have our own desired bioisosteric replacements. I'll just close that and have a look at some of the other results that have been written to the output database. So here you can see that we've got some calculated properties along with the score that's been written to the output database. This being an energy, the more negative that value becomes, the better the interaction between the ligand and the receptor. So now that we've generated a handful of results, I'm just going to stop the calculation. In fact, it's finished already. So let me go to the database viewer and we'll browse to have a look through some of these results. So I'll just open the browser, which will allow us to view the replacements in 2D and 3D simultaneously. So here we see the 2D schematic, and we can write some of the fields that we have here. So for example, I might want to write the score so I can keep track of that in the database viewer and as well in the main Mo window. In the main Mo window itself, we can see the newly generated structures shown in green relative to the original co-crystal ligand shown in cyan. And from here, I can just cycle through to have a look at some of the replacements that we've generated today, which allows us to diversify our chemistry whilst largely retaining the original properties of the ligand. So I'll just close our browser and bring back the original panel to wrap up that today we've been using the medicinal chemistry operation to perform bioisosteric replacements to a ligand in a 3D receptor pocket. This is a useful application for when we want to make minor and focused changes to our structure. I hope that you've learned a lot today. If you have any questions, please do reach out to me at support@chemcomp.com.